Welcome to Magnetized Labs. Today we are going to see the design of DC motor driver using DRV8701 in KiCAD. First we will see the schematic, then we will see the PCB, then we will go to the 3D part. Before that we will see the outline of the project. Here we are using DRV8701 H-bridge controller from Texas Instruments, which is used to drive the H-bridge MOSFET, and this whole design is used to drive the DC motor with respect to the PWM and direction inputs, and we have power and fault indication LEDs in the board. What is DC motor driver? A DC motor driver is an electrical module controlled by electronic circuits used to drive direct current motors. And how it works? It works by changing the polarity of the power supply to the motor as a H-bridge configuration, which in turn changes the direction of the rotation. When it comes to the specifications part, this board can take up to 45 voltage DC input, and it can give the output of massive 29 amperes of load current. The signal type is actually compatible for 3.3 volt and 5 volt logic, and this can be only driven with PWM input. Analog control is not possible. If you want to add analog control, you have to add an external circuit. The maximum PWM driving frequency is 100 kHz. We will go to the schematic now. We have used M3 hole footprint as an input connector because we need to actually carry a whole lot of current around 30 amperes, so that you can use very thick wires with U-lug or round lug to connect into M3 screw and nut. This design also features a reverse polarity protection, which means when you connect positive input wire to the negative terminal and the negative input wire to the positive terminal, this board will not blow up. Instead, it will automatically turn off the board because there is no current flow when you connect the polarity in reverse manner. For that, we have used a P-channel high current MOSFET and a Zener diode of 12 volt rating. When you drive a DC motor using a motor driver, the motor will take very large current at the initial stage. To support that large high current input, we have added 4 number of 220 microfarad capacitors, and then we have added a power indication LED. When it comes to the H-bridge controller, we have chosen DRV8701 model from the Texas Instruments. It has two versions. One is DRV8701E and the another one is DRV8701P. This DRV8701E version comes with enable and phase control of the H-bridge, and the DRV8701P version comes with PWM1 and 2, which is actually direct PWM pins of the H-bridge driver. For the easier control and the convenience of the interface, we have actually used the DRV8701E version. Now we will see the design part. First pin is VM pin, which is the supply pin for the H-bridge controller. Up to 45 voltage DC, this pin can handle. And then the second pin is charge pump output pin. So as per the datasheet recommendation, we have connected this pin to VM through 1 microfarad ceramic capacitor. Third and fourth pin are charge pump high and charge pump low pins. As per the datasheet recommendation, we have connected 0.1 microfarad high quality ceramic capacitor. Seventh pin is AVDD, which is a 4.8 volt analog supply regulator pin. Eighth pin is DVDD, which is 3.3 volt digital logic supply regulator. These two pins, AVDD and DVDD, should be decoupled with high quality 1 microfarad ceramic capacitor. 14th pin is the enable pin for the H-bridge. This can be used as a PWM input, and the maximum PWM driving frequency is 100 kHz. 15th pin is the phase control of the H-bridge, which can be used to change the direction of the motor. Both enable and the phase pins has its own internal pull-down resistors. These both pins will decide the direction and the speed of the DC motor. Speed will be controlled by the PWM and duty cycle, and then the direction will be controlled by the phase pin. 13th pin is end sleep pin, which is used to put the H-bridge controller in low power sleep mode and all the H-bridge MOSFETs in high impedance state. According to the datasheet, I have connected this end sleep pin to DVDD to put this H-bridge controller in active state. 12th pin is high drive pin. This pin is used to set the source and sink current of the H-bridge MOSFET driver inside the controller. I have connected this pin to AVDD through 68 kilo ohm resistor to set 150 milliamperes of source current, 300 milliamperes of sink current. Of course, there are other source and sink current combinations are available. You can check it in the datasheet. Accordingly, you can change this configuration. Before explaining this SO pin, we will first check this V reference pin and then we'll come back to this. VRF pin is used to set the current limit of the whole circuit, which is set to 29 amperes. When it comes to the current sensing part of the H-bridge controller, this is how the internal circuit will be. We have used 5 milliohm R sense, which is the current shunt resistor, which will be connected to the internal op amp that is having the voltage gain of 20. This pin is an SO pin. This is the sense output. This, when you are using the microcontroller, you can connect this pin to your ADC and then you can measure the current according to these calculations and the current sense resistor value you have used. This VRF pin is used to set the current limit threshold. We have set 2.914 voltage through AVDD pin with the potential divider. When the voltage at this pin crosses 2.914, this H-bridge controller will put the device into current limit mode and then it will go into overcurrent protection. Now assume 30 amperes of current is flowing through this resistor and then you will get the voltage drop of 150 millivolt across these SP and SN pins, and it will be amplified 20 times and then it will be fed to this comparator. Now 150 millivolt into 20 is around 3 volts. So when it crosses 2.914 voltage, this comparator will trigger the overcurrent protection mode. So the set limit is 29 amperes. Yes, that is how this circuit works. 10th pin is SNS out. This pin is an open drain configuration. This pin is used to denote the H-bridge controller went into current chopping mode when it crosses the current limit. 9th pin is N fault pin, which is also an open drain configuration pin. This pin is used to denote any fault which is detected by the H-bridge controller. We have connected an LED. This will come up when any fault indicated by this H-bridge controller. This circuit is logic inverter circuit. When we are giving direction high, this phase pin will go low. The H-bridge will go into reverse drive direction. When this pin is low, this phase pin will be high. So this will be driven in forward direction. For the ease of interface, we have actually added this circuit as well. For the signal inputs, we have added a small connector for PWM and direction. Also, we have added the mounting hole for the PCB board. Output connector is again M3 hole pad connector, which is very convenient to connect high current wires with round lug and U-lugs. When it comes to the H-bridge power stage, we have used 2 power MOSFETs in parallel to support the high current capability, and we have used separate gate resistors, separate gate to source resistors for each and every MOSFET to avoid false turn-on of a single MOSFET in the leg, which will cause the entire current to flow in one MOSFET, and it will increase the power dissipation in a single MOSFET and the temperature as well. We have used 5 milliohm precise current sense resistor to measure the current to the load through H-bridge. This is actually connected to the H-bridge controller through 10 ohm series termination resistors to avoid noises in the current sensing circuit. Also, these traces are routed as a Kelvin sense to achieve accurate current sensing. That's about the schematic. Coming to the layout, this PCB has a mounting hole at each corner for convenient mechanical mounting. This PCB is having the dimension of 68 mm length and 41 mm width. Starting from the input connector, which is a M3 hole pad connector, which is directly connected to the P-channel MOSFET, which is used for reverse polarity protection. The output of that is directly connected to the input electrolytic capacitors, and then it is connected to the drain of the high side MOSFETs of the H-bridge circuit. And then the signal input connector, PWM and direction. PWM is directly connected to the H-bridge controller IC. Direction pin is going through the inverter circuit and to the H-bridge controller. Fault indication LEDs, power indication LED. To support the high current capability, we have used 4 layer stackup. The output connector is connected to the H-bridge circuit via internal layers. We have provided enough number of thermal wires to support the power dissipation and the temperature regulation of the board. This current sense resistor is just placed near to the low side MOSFETs of the H-bridge and routed to the H-bridge controller via differential Kelvin sense routing. Now we will go to the 3D part. Have a look at the 3D view of the design. Input connector, M3 hole pad, M3 screws and nuts, P-channel reverse polarity protection MOSFET, and input electrolytic capacitors, H-bridge MOSFETs with the current sense resistor, and then output connector again M3 hole pad with M3 screws and nuts, H-bridge controller, inverter circuits for direction, input signal connectors for PWM and direction, fault indicator LEDs, power indication LED. I have kept very few resistor at the bottom side, and then the logo and the title of the project, almost like a simple design. There are a lot of protections available in the design. Undervoltage lockout. When the input voltage goes below 6 volt, the H-bridge controller will disable its operation and it will indicate through the fault indicator LEDs. Charge pump fault, overcurrent shutdown, short circuit protection, free driver fault, over temperature fault, and finally reverse polarity protection, which we added externally. This DC motor driver has a wide range of application in different sectors: robotics, automotive systems, industrial automation, especially in factory and warehouse automation, home appliances, drone and RC vehicles, consumer electronics and DIY projects, battery powered devices, and much more. We have included the schematic and the BOM of the design in the description for your reference. If you have any queries or feedback or any improvement points, please let us know in the comment section. We would love to hear from you. Thank you.